Alright, welcome to EE16B video notes for transient analysis. So in one of the other previous video notes, Sid talked about how to solve very generic differential equations, how we want to solve those. Here we are going to take those and apply it to very specific examples of circuits and transient analysis. So basically what happens, how capacitors charge and discharge, and what is happening in a small period of time before things actually become steady state. So we're going to start off with a simple motivating example, which was actually part of the homework, I believe. So we're going to have a voltage source at voltage VDD, and then connected to it via a switch. We just have a capacitor and a resistor. These are all connected, and this is grounded. So at time t equal to 0, this switch flips up, and then you're left with the capacitor and resistor. So we're going to call this C and R. Those are the values, and then plus and minus VC. And this is, this is IC flowing into the capacitor. Okay, so what I like to do when solving these problems is to first think about intuitively what is happening with the capacitor and what the initial conditions and the final solutions should be, and so that once we solve it, we can think that we can ask ourselves if it fits what our intuition says. So let's start off and just draw a graph of what's happening. So at time t equal to 0, we know that VC, the capacitor, should be fully charged. So this should start off at the voltage VDD. So this is t equal to 0. So at all times t is less than 0, then the capacitor should be at VDD. Something happens in the middle. We're going to be figuring out what that something is. But after the switch is flipped, we're just left with the resistor and capacitor. Therefore, at some large time, we know that it'll settle down to its final value at V equals to 0. The capacitor should fully discharge through the resistor, and we're left with a discharged capacitor at some time. Now the question of transient analysis is what happens in this middle period. Happens here. So to answer that question, we need to look at the differential equations. Okay, so how do we solve this? Let's first look at the capacitor voltage relations. So we know that IC should equal to C dVC dt, where VC is the voltage across the capacitor and IC is the current going into the capacitor. Okay, so we have this, and then our circuit looks like the following. So once the switch is flipped, we're just left with this, so C and R. So how do we solve this equation? Great. So as you can see here, we have one equation with two variables. We have IC and VC. Those are our two unknowns that we're trying to solve for. So obviously we can't solve one equation with two unknowns. So we need to have some other relationship with the current and the voltage. So to do that, we need to look at the circuit. Let me actually draw this a little bit bigger so we can mark it up. Okay, so capacitor, resistor. Let's define IC going into the capacitor, and then plus and minus VC across the capacitor. So I do it like this so that this still holds. If I wanted, if I defined IC going the other direction, so for example, if I decided I want an IC going this direction, then this would actually be negative. But just for the sake of clarity, I always like to define my current directions going into the capacitor so that I don't have to deal with that negative sign. So we're going to call it that. Okay. So from here, we know that if this is plus and minus VC is also across the resistor. So we can note that from V equals IR, Ohm's law, we can say that VC over R equals minus IC. So this is because the current is going in this direction out of the resistor, and our voltage is plus and minus across the resistor. Therefore, this should have a negative sign. We plug that back into the equation above, and we can see that minus VC over R equals C dVC dt. And moving everything around, VC equals minus RC dVC dt. This looks exactly like the eigenvalue equation that we had seen before, and we know how to solve this. Great. So this is our an eigenvalue equation. So we take this and we say that VC, it should be some sort of exponential function. So VC equals V of 0 e to the lambda t. So what is this? Let's plug it back in into this equation. So we have V of 0 e to the lambda t equals minus RC V of 0 lambda e to the lambda t. This is from taking the derivative. The V of the lambda comes down, and so this goes away, this goes away, this goes away, this goes away, and we can see that lambda equals minus 1 over RC. So now we have VC of t equals V of 0 e to the t minus t over RC. Okay, so now what is this V of 0? This is the initial condition that we were talking about before. Why did I talk about this at all? Because our equation isn't fully defined without this initial condition. So to solve for that, we know that VC of 0 equals VDD from our analysis before. Therefore, VC of t equals VDD e to the minus t over RC. Okay, now for a quick sanity check. We said that intuitively we want it to start off with VDD and then end at 0. Does this satisfy that? So let's do a quick graph. So at time t equal to 0, it starts off at VDD, check, because e to the 0 is 1, and therefore VC of 0 is just VDD. This is just a decaying exponential, so as time moves on, this becomes just a smaller and smaller value. So it goes like this, and then eventually it just approaches 0. Okay, and from our sanity check, we can see that this t equals 0, and this is t equal to infinity. It approaches the 0 value as we wanted it to. So this works. This is a first simple motivating example, and I'll go more into RLC, a more in-depth example soon.